Dr. M. P. Jayaraman is an assistant professor in mathematics in L.N. Government College, Poneri. He has specialized on geometric function theory. With 14 years of teaching experience, he has handled topics on probability and queuing theory, discrete mathematics, random process, and engineering mathematics. Being a recognized supervisor for guiding PhD and MS students of Anna University, he is the reviewer of the journal Computer Mathematics and Applications. He has also written books on discrete mathematics and has also published papers in 28 international publications, in 4 national publications, and has presented papers in 2 international and in 2 national conferences.
Welcome you all for UGC lecture series in mathematics. In this session, we are going to solve the given quadratic programming problem using Wolf's method. We have seen that in Wolf's method, to solve a quadratic programming problem, first we have to derive the Hundecker condition for the given quadratic programming problem. Then by introducing a new set of non-negative artificial variable, we have to construct a new objective function so that the given quadratic programming problem can be converted into linear programming problem. Finally, by applying two-phase simplex method, we will try to get the optimal solution to the given modified linear programming problem, which also satisfies the complementary slackness conditions. Thus, optimal solution which satisfies the complementary slackness condition is the optimal solution to the given quadratic programming problem. Using Wolf's method, solve the quadratic programming problem. Maximize z equal to 4x1 plus 6x2 minus 2x1 squared minus 2x1 x2 minus 2x2 squared, subject to the constraints x1 plus 2x2 less than or equal to 2, x1 x2 greater than or equal to 0. We have seen that by deriving the Hundecker condition to the given quadratic programming problem, the linear programming problem becomes minimize z equal to minus a1 minus a2, subject to the constraints 4x1 plus 2x2 plus lambda 1 minus mu 1 plus a1 equal to 4, 2x1 plus 4x2 plus 2 lambda 1 minus mu 2 plus a2 equal to 6, and x1 plus 2x2 plus s1 squared equal to 2, and lambda 1 s1 equal to 0, mu 1 x1 equal to mu 2 x2 equal to 0. This set of conditions are called complementary slackness condition. Now, from this modified linear programming problem, we got the initial basic feasible solution as a1 equal to 4, a2 equal to 6 and s1 equal to 2. We try to improve the optimal solution from this initial basic feasible solutions. For that, we have to go for two-phase simplex method. In two-phase simplex method, we have to get the initial solution to the given linear programming problem. So, for the equations, we have seen that the initial table is nothing but this one. So, a QPP can be converted into linear programming problem. For that linear programming problem, from the initial basic feasible solution, we got this initial iteration, which is the initial solution of the given QPP. Here yb is the basic variable for the given quadratic programming problem. By introducing the artificial variable a1, a2, we get our basic variable as a1, a2 and s1. The cost of a1 is minus 1 and cost of a2 is minus 1 and s1 cost is 0. So, CB is the cost of the basic variable, and the solution value for this basic variable is 4 for a1, for a2 6. Now, the values for the basic variable s1 equal to 2, and by collecting the corresponding coefficient, we will get the initial simplex table as this way. Now, we try to improve the optimal solution for the given linear programming problem. So, in order to get the optimal solution, the condition is we have to check all Zj minus Cj should be greater than or equal to 0. If all Zj minus Cj greater than or equal to 0, then optimal solution is obtained. Here Zj is summation Cb Yj, j varies from 1 to n minus Cj greater than or equal to 0. If all Zj minus Cj greater than or equal to 0, optimum solution is obtained, otherwise we have to improve the optimum solutions. Now, for this initial table, first we try to compute Zj and Cj, then we compute Zj minus Cj. Now, Zj is Cbyj. So, for the variable y1, my Zj is minus 1 into 4 plus minus 1 into 2, which is minus 4 minus 2. Therefore, I am getting it as minus 6. Then, for y2 variable, my Zj is minus 1 into 2 plus minus 1 into 4 minus 6. In the same way, Zj value for lambda 1 is minus 3, and for mu 1 is minus 1 into minus 1 plus minus 1 into 0, which is plus 1. For mu 2 is also 1. Since a1, a2, s1 is in the basis, the Zj minus Cj value for this basic variable s1, a1, a2 is always 0. Therefore, no need to compute Zj and Cj value for this variable, it will always 0. Zj minus Cj for this basic variable is 0. Now, cost for this variable y1 is 0, y2 is 0, lambda 1 equal to 0, mu 1 equal to 0, mu 2 equal to 0. Therefore, the cost for Cj value is 0, 0, 0 for lambda 1, for mu 1 0, mu 2 0. Now, Zj minus Cj value is for y1 minus 6, for y2 also minus 6, for y3 that is lambda 1 minus 3, for mu 1 it is 1, for mu 2 it is 1. So, if all Zj minus Cj greater than or equal to 0, optimal solution is obtained. For this initial iteration, if we observe Zj minus Cj value, Z1 minus C1 equal to minus 6 negative, Z2 minus C2 is minus 6, Z3 minus C3 is minus 3. Since not all Zj minus Cj greater than or equal to 0, all Zj minus Cj value is not greater than or equal to 0. Therefore, for this table the optimal solution is not obtained. So, we have to improve the optimal solutions. So, in order to improve the optimal solutions, from all Zj minus Cj value, we have to choose the most negative. We have to choose the most negative value. So, among all Zj minus Cj value, the most negative value occurs corresponds to y1, which is minus 6, and y2 minus 6. So, among these two value, we can choose any one value. Here for this problem, the complementary slackness condition is mu 1 x1 equal to mu 2 x2 equal to 0. Since mu 1 is not in the basis, we can choose x1 in this one. So, I can choose this variable minus 6. So, the variable y1 is entered in this basis. The variable y1 is entered in the basis. Now, the variable y1 is entered into the basis. Once we fix the entering variable, next we have to compute the ratio of minimum of xbi by yir, where yir value should be positive. Therefore, for this entering variable xb is 4. So, 4 by 4 we have the value as 1. Then for the second one xb value is 6. So, 6 by 2 we have 3. Now, for the third one xb value is 2 and yir value is 1. So, 2 by 1 is 2. So, once we fix the entering variable, here our entering variable is y1. Once we fix the entering variable, compute the ratio minimum of xbi by yir where YIR should be positive. So, for this table y1 is the entering variable. For this y1, if we compute xbi by YIR, that is 4 by 4 1, 6 by 2 3, 2 by 1 2. Among all this ratio, we have to choose the minimum value. Among 1 3 2, the minimum value is 1. Therefore, we have to choose this value. Therefore, the corresponding variable is a1. Therefore, a1 is the leaving variable. For this table, y1 is our entering variable. y1 enters the basis. So, y1 enters to the basis, and by computing the minimum ratio occurs for a1. Therefore, a1 is the leaving variable. So, y1 enters the basis and a1 leaves the basis. Where the entering variable and leaving variable intersect, no, such point is called pivot element. Here y1 and a1 intersect at this place 4. Therefore, for this table is pivot element is 4. So, the initial iteration, our entering vector is y1, leaving vector is a1 and pivot element is 4. Now, in order to improve the optimal solution to the given linear programming problem, next step is we have to convert the pivot element is 1. For this table, this 4 is our pivot element. So, in order to improve this basic feasible solution to an optimal solution, now we have to convert this 4 into 1 and the remaining element in that column as 0. Therefore, we have to convert this 2 as 0, this 1 as 0. So, in order to improve the optimal solution, the next step is we have to convert the pivot element as 1 and remaining element in that column as 0. Now, to convert this pivot element 4 as a 1, we have to divide the entire row by 4. So, if we take new row as R1 dash, by dividing R1 by 4, we will get our R1 dash as 1, 1, 2 by 4 which is 1 by 2, 1 by 4, minus 1 by 4, 0, 0, 1 by 4, 0. So, this pivot element is converted as unit element 1. Our next idea is we have to convert the remaining element in that column as 0. So, I have to convert this element 2 as 0. For that, the elementary operation R2 dash is nothing but from R2 I have to subtract 2 R1 dash. So, my R2 is 6, 2, 4, 2, 0, minus 1, 0, 0, 1. From this R2, the newly obtained R1 dash, I have to multiply this by 2. So, 2 into 1, 2, 2 into 1, 2, 2 into half which is 1. Then if we multiply this 2 by 4 which is becomes 1 by 2, then minus 2 by 4 which is minus 1 by 2, 0, 0, 2 by 4 which is 1 by 2, 0. So, in order to convert this 2 as 0, I will subtract 2 R1 dash from R2. R2 is the given row, R1 dash is the row newly obtained. By multiplying this row by 2 and subtract 2 R1 dash from R2, we are getting the following: 6 minus 2 4, 2 minus 2 0, 4 minus 1 3, 2 minus 1 by 2 which is 3 by 2, then this will become of minus 1 0 minus of 1. So, by making use of the row elementary transformation R2 minus 2 R1 dash, I will get the value as 4 0 3 3 by 2 1 by 2 minus 1 0 minus 1 by 2 1, which is our new R2 dash. Now, if you observe, the value corresponds to y1 which is 0. So, by this elementary transformation this 2 becomes 0. Now, the next idea is we have to convert this 1 into 0. For that, the elementary operation is our new R3 dash is nothing but from R3, if we just subtract our R1 dash, we will get this value as 0. Now, our R3 is 2, 1, 2 0 0 0 1 0 0. This is our R3. Now our R1 dash is this one 1 1 1 by 2 1 by 4 minus 1 by 4 0 0 1 by 4 0. So R3 minus R1 dash gives us 2 minus 1 1 1 minus 1 0. This is 2 minus 1 by 2, which is 3 by 2 minus 1 by 4 plus 1 by 4 0 1 minus 1 by 4 0. Now in this R3 dash, if we observe the coefficient corresponds to y1, which will become 0. So in such a way, we by making use of the row elementary transformation, we will convert the pivot element 4 as 1 and remaining element in that column as 0. Let us have a break. Welcome back. Before break, we discussed about solving procedure of a quadratic programming problem. Now we will try to continue to obtain optimum solution to the given problem. From the initial table, now we will convert this pivot element as 1 and remaining element in that column as 0, which precisely given in the next table. So by converting the pivot element 4 as 1 and remaining element in the column as 0, we will get this table. Now in the previous table, y1 enters the basis and a1 leaves the basis. So in the iteration 1, instead of a1, we should replace the basic variable a1 by y1. Therefore in this table, in the place of a1, we will replace a1 by x1. So in the previous table, a1 leaves the vector and y1 enters the basis. Therefore in the place of a1, we will put the variable x1, remaining variable as it is. So a2 is also in the basis, s1 is in the basis. Now the cost of x1 is 0 and cost of a2 is minus 1 and cost of s1 is 0. So in this table, again we have to check the optimal condition. For that, we have to compute zj and cj value. So zj, cj, then zj minus cj value. Now for this table zj, now in this table x1, a2, s1 are in the basis. Therefore no need to compute zj minus cj value for x1 and no need to compute any zj minus cj value for a2 and for s1. Since x1, a2, s1 are in the basis, the zj minus cj value for those variables x1 is 0, s1 is 0, a2 equal to 0. Since in the previous table a1 leaves the basis, in iteration 1 we no need to compute the a1 value for the a1 variables. So we no need to compute a1 in this iteration 1. Now for y2, our zj value is 0 into of plus minus 1 into 3. So we have minus 3. Then for lambda 1, 0 into minus 1 by 4, 0 into minus 1 by 4 plus minus 1 into 3 by 2. So we have minus 3 by 2. Then for mu 1, we have minus 1 into of, we have minus of. For mu 2, we have 0 into 0 plus minus 1 into minus 1. So we have plus 1. That's all. Then cost for y2 is 0, cost for lambda 1 is 0, mu 1 is 0, mu 2 is 0. So zj minus cj value is minus 3 comma 0 minus 3, then minus 3 by 2 minus of 1. That's all. So now we have to check whether all zj minus cj greater than or equal to 0. In order to check the optimality condition, we have to check this condition. Now for this table 1, if we observe zj minus cj, not all zj minus cj value greater than or equal to 0. So still optimum solution is not obtained. So now we have to improve the optimal solution. If we observe the zj minus cj value, there are 3 negative values are there, minus 3, minus 3 by 2, minus 1 by 2. Now, among all these 3 negative value, we have to choose the most negative. The most negative occurs corresponds to y2, which is minus 3. Therefore, we have to choose this variable. So, in the first iteration our y2 enters the basis. So, y2 enters the basis. Now, once we fix the entering variable y2, for this y2 we have to compute the minimum ratio xbi by yir, where yir is positive. Therefore, for y2 xb value is 1. So, 1 divided by 1 by 2, which is 2, 1 by 1 by 2, which is 2. Now, for the second one we have 4 by 3, which is 1.3 something. Then the fourth one 1 divided by 3 by 2, which we have 2 by 3, which is 0.6 something. So, among all xbi by yir, the minimum occurs here, the corresponding variable S1, therefore, S1 leaves the basis. So, for this table the entering vector is y2, y2 enters the basis and S1 leaves the basis. So, y2 is entering the basis and S2 leaves the basis. So, where y2 and x1 intersect, this element is called pivot element, which is 3 by 2. So, for this table the entering vector is y2, y2 enters the basis. So, y2 enters the basis and S1 leaves the basis. So, S1 is the leaving vector. Therefore, these two vectors intersect at this point 3 by 2. Therefore, for this table pivot element is 3 by 2. Now, next idea is, as we proceed earlier, we have to convert this pivot element as 1. So, we have to convert this pivot element 3 by 2 as 1 and remaining element in that column, that is in that column the remaining element 1 by 2 as 0 and 3 as 0. We have to improve the optimal solutions. So, by converting this pivot element as 1 in the remaining element as 0, we can get the next iteration. So, as proceed earlier, by taking this as R1 dash and R2 dash and R3 dash, now we can convert this element as unit by dividing the entire row R3 dash by 3 by 2 or multiplying by 2 by 3. So, by dividing the entire row R3 dash by 2 by 3, we will get R3 double dash. So, that this 3 by 2 becomes 1. Now, we have to make the remaining element in that column as 0. To make this 3 as 0, what we have to do now? From R2 dash, by multiplying this R3 dash by 3 and subtract 3 R3 double dash from R2 dash, we convert this 3 into 0. Next, we have to make this 1 by 2 as 0. For that, from R1 dash, if we subtract 1 by 2 R3 double dash, this entry becomes 0. So, by making use of row elementary transformation, we can convert this pivot element as 1, remaining element in that column, this 3 as 0, this 1 by 2 as 0, which we display in the next table. So, by converting that pivot element as 1, remaining element in that column as 0, we will get the iteration 2. Now, for this iteration, we have to check all Zj minus Cj greater than or equal to 0 or not. So, for that we have to compute Zj minus Cj for this one. So, for this table our Zj is Cj and Zj minus Cj. Now, in the previous table y2 enters the basis and S1 leaves the basis. Therefore, in the place of S1 we have to put the variable y2. Now, in the place of S1 we introduce the variable x2. Therefore, in iteration 2 x2 is in the basis. So, in iteration 2 x1 is in the basis, a2 is in the basis and x2 is in the basis. Now, for this iteration we have to compute Zj minus Cj value. So, since x1, a2, x2 is in the basis, no need to compute zj minus cj value for x1, x2 and a2. Now, for lambda 1 our zj value is 0 into 1 by 3 plus minus 1 into 2. So, we will get it as minus 2. So, in similar way for mu 1 zj value is 0, for mu 2 zj value is 1. The cost of this variable is 0, 0, 0, and for S1 this is 0 into minus 1 by 3 minus 1 into minus 2. So, we will get 2 as zj value is 0. Now, if we compute zj minus cj, we have z1 minus c1 as minus 2, 0, 1, 2. Now, in order to get the optimal solution, we have to check the condition all zj minus cj greater than or equal to 0. Now, except z1 minus c1 all are positive. So, here not all zj minus cj greater than or equal to 0. The z1 minus c1 is negative, therefore, optimal solution is not obtained. Now, we have to improve again this optimal solution. For that, we have to choose the most negative. Here only one negative is there, therefore, we have to choose this value. Therefore, lambda 1 is the variable which enter into the basis. Once we fix the entering vector, next we have to compute the minimum ratio xbi by yar, where yar positive. For this one 2 by 3 divided by 1 by 3. So, we have 2. Then for this one 2 by 2 we have 1. Now, for this one the condition for xbi by yar is yar should be strictly greater than 0, but here yar is negative, therefore, no need to compute this ratio for x2, therefore, this takes no value. Now, once we fix the entering vector lambda 1, if we compute the minimum ratio xbi by yar, for this one 2 by 3 by 1 by 3 which is 2, for this one 2 by 2 which is 1, for this since yar is negative, we should not compute this value. Among this one minimum is 1. So, our leaving vector is a2. So, in iteration 2 our entering vector is lambda 1 and leaving vector is a2 and the corresponding pivot element is nothing but this 2. So, in iteration 2 our lambda 1 enters the basis, a2 leaves the basis. So, the corresponding pivot element is 2. Now, the next idea is we have to convert this pivot element as 1 and remaining element in that column as 0 with the help of row elementary transformation. In iteration 3, x1, lambda 1 and x2 are in the basis, therefore, zj minus cj value for those variables are 0. Now, for mu 1 zj value, since the cost of all the variable x1, lambda 1, x2 equal to 0, our zj value for mu 1 is 0, mu 2 is 0, s1 0, and cost for this basic variable is 0. Therefore, our zj minus cj is 0. Now, in iteration 3, we are getting all zj minus cj value is greater than or equal to 0. Here all zj minus cj greater than or equal to 0. Therefore, optimum solution is obtained. Since all zj minus cj greater than or equal to 0, optimal solution for this linear programming problem is obtained, where our optimal solution is x1 equal to 1 by 3, lambda 1 equal to 1 and x2 equal to 5 by 6. So, optimal solution to the linear programming problem is x1 equal to 1 by 3, x2 equal to 5 by 6, lambda 1 equal to 1, all the remaining variable lambda 2, mu 1, mu 2, s1 values are 0. Now, this optimal solution satisfies the complementary slackness condition mu 1 x1 equal to 0, mu 2 x2 equal to 0 and lambda 1 s1 equal to 0. Moreover, all this value satisfies the restriction on Lagrangian multiplier. Therefore, maximum z star equal to 0 is the feasible solution. Therefore, the optimal solution obtained for the given linear programming problem is the optimal solution to the given quadratic programming problem. Now, by substituting this x1, x2 and lambda 1 value in the given quadratic programming problem, we will get our optimal solution as maximum z equal to 25 by 6. So, using Wolff's method, we can obtain optimal solution to the given quadratic programming problem. So, the Wolff's algorithm is, first we have to derive the Hundecker condition for the given quadratic programming problem and convert the given quadratic programming problem into linear programming problem. Then with the help of two-phase simplex method, we can obtain optimal solution to the given linear programming problem, which satisfies the complementary slackness condition, which is the optimal solution to the given quadratic programming problem. Thank you.